All right, welcome everyone. Thank you for coming. It's exciting to kick off this tutorial on a very long title, Data-Driven Methods for network level coordination of autonomous mobility on demand systems across scales. So it's even an extra one. So the point of references for this tutorial are sitting in the front row. So there's me, nice to meet you, I'm Gioele. There's Daniele Gammelli from Stanford, Caroline Schmidt from DTU, and there's Maximilian Schiffer from UM. And there are others, the others that you see the pictures of are online and are supporting the online audience. So let's make this very interactive. The idea is that we give a tutorial about the basics of data-driven control for this class of systems. So the battle plan for today is that we will have first an introduction and logistic, actually together with it's me and Daniele. Then Daniele will give a primer on graph reinforcement learning. There's going to be a talk from Max Schiffer on multi-agent reinforcement learning or something related to that. There's going to be then a talk from Caroline on offline RL, talking also about the robustness and scalability. Then we're going to have a coffee break. And after the coffee break starts the kind of interactive part. We will have a small talk from Luigi Tresca about benchmarking. And then we have an interactive activity for you to play a bit with the concepts we will have introduced along the way. At any point, if you have questions, stop us, ask. We are trying to grow this community. So don't be afraid of asking questions. There's no stupid question. Okay, so why are we here? I thought of giving a very, very short overview, but the idea is that we are presenting today a technology that could contribute to solving some of these problems. We're not selling this as a unique technology. You know, it's going to be a mix of many things. But in general, we are observing that travel demand is increasing, especially in cities. You have these new services like Uber or in general ride-hailing companies. And finally, we also have to strive to get better at fulfilling sustainability goals. And in this context, if you think about producing a car, we move from the concept of a mass-produced car, where the idea was these cars are faster than horses, to something fancier, where the car becomes a consumer product, so it is a synonym of lifestyle and status, to these fancy things, these fancy autonomous vehicles or cars without a driver that could improve sustainability, safety maybe, and also convenience. And the particular technology we're talking about today is not necessarily autonomous vehicles per se, but it's autonomous mobility on demand. So fleets of autonomous vehicles that are centrally controlled to serve multiple demands. So we're really going towards the benefits of this technology. And in this technology, in the past years, there has always been two sides of the story. Depending on how you implement this technology, you might have the heaven or hell situations. Just for the sake of going through the basics of this, some people observe that cars in most cities are parked for most of the time. Most cars are on the road at the same time. You know, you have this idea of peak hours when people have to go to work, for instance. And autonomy, so if you increase the benefits of traveling with private cars, that might increase congestion. You know, if you make traveling with this kind of cars better and easier, this could have drawbacks. On the other hand, there are studies that show that you could reduce by a lot the number of cars on the road with this technology. And second, that by having higher utilization of cars, you could reduce congestion. There is also the idea of public versus private. You know, private ownership of vehicles might have as a consequence these many cars around orbiting, waiting for customers, these so-called zombie cars. And Uber-like services might have a negative impact on the long term for public transit as well. On the other hand, there are studies that show that first and last mile connectivity could be improved with such services and make public transit more accessible. And on the other hand, trains and buses could be good when they are full, but those services could complement these situations, these regimes where you cannot fill the public transit service. In terms of societal impact, There's a lot of people criticizing autonomy in general, saying all taxi and bus drivers will be out of jobs, or only rich people will afford them. But actually, you can also show that in some situations, you can make mobility services first of all, more affordable, but also that you could break the cycle of having manpower limitations. Right now, there are studies that show that 1 in every 7 humans would need to be a driver if we continue urbanizing cities as we do right now. So we have many scales at play in what you will see today. There is ideas of developing a single vehicle, of putting them into a fleet, and then interacting with existing infrastructure. You will see things like charging vehicles and so on. And in general, we will look at 3 main problems. The first one is called dispatching. Essentially, this is the idea of you have a set of people that want to travel from certain A's and certain B's, and then you match people with vehicles, okay? There are various versions of this, but this is generally what we call dispatching or matching. Then there is the thing called routing, which is once you matched passengers with vehicles, you decide how to route them to their destination. And there is some degree of freedom. And finally, a very important one, it's called rebalancing. You don't want to just assign passengers and route them, but also be proactive and think about where demand might be and rebalance your fleet such that you will be more reactive to changes in demand. There is another one which is very interesting. We will not necessarily touch this a lot today, but it's called ride sharing. And this gives the ability to a car to have more passengers and different routes and different interests. So combining multiple trips together. Now, there is a big ecosystem. You will see today, we're trying to standardize a bit of some of these things, but you will have all these problems, dispatching, routing, rebalancing, and ride sharing. Sometimes you have constraints that limit this. For instance, upkeeping, charging the vehicles, calibrating the vehicles, and so on. Those can be very challenging. Or even operational constraints, like an electric vehicle can only drive as many miles, and so on. Then there are other factors that are not on the operations, but are on the planning side, like deciding the kind of vehicles you want to have in your fleet, how large you want the fleet to be, and what kind of autonomy level you care about, so the speed at which you can drive, but also the interactions with infrastructure. You will see something like charging stations, parking, and calibration. And now those are, so to say, the problems, and then comes how to model these problems and how to solve them. And here there are all sorts of things. There are models that are important for modeling the transportation network. Here there could be graph theory, queuing theoretic ones, continuum ones. You could think about modeling the demand, elastic, inelastic. You can think about operational constraints such as charging, the fleet sizes, parking, and interactions with infrastructure. And solutions are typically leveraging mathematical optimization, custom algorithms, or data-driven solutions. And today we will sit at the interface of learning and mathematical optimization. Okay. And now this is a perfect time to hand the words to Daniele. So in the spirit of mixing these 2 classes of solutions and teaching you how this can be employed in real settings, it will continue giving you a primer of reinforcement learning, and then all the sessions will be motivated further. But thank you for coming, guys. Thanks.